Welcome to this lecture series in real analysis. Last time we defined the field of real numbers. We defined it as an ordered field which has the least upper bound property. That was the definition. And we then made two remarks. The first was about the existence, meaning there does exist a field, an ordered field with the least upper bound property, which is to say that every non-empty subset of it which has an upper bound also has a least upper bound. And then we said that such an object is unique. There is only one such object in a certain sense that we mentioned. We gave a definition to that uniqueness or an exposition to it. In this lecture, we will be proving the first remark. We will be actually constructing a field, an ordered field with the least upper bound property. And about the uniqueness, we will not be discussing it explicitly. As this course progresses and as you learn more and more about real numbers, you can understand that remark better and better. So you can take that as an ongoing exercise. With that, let us recall a few things. So we need to know what are rational numbers. We need to know the meaning of a least upper bound. We saw a deficiency in rationals where there was a subset of rationals which had an upper bound but no least upper bound inside the rationals. Then we defined what are fields and ordered fields to abstract out all the properties of rationals. We saw that every ordered field has a natural copy of the rationals in it. And finally, we defined real numbers as an ordered field with the least upper bound property. Okay. So, to construct the field of real numbers, we will take the approach developed by, as far as I know, it was developed by a mathematician named Dedekind. I think it was Reinhard Dedekind, but anyway, I don't know the exact name. It is R. Dedekind. And you can find a detailed exposition of it in this reference, Principles of Mathematical Analysis by Walter Rudin, 3rd edition, appendix to chapter 1. So I am following this. I will not be giving all the details. For one, this is an optional lecture in the sense that we do not need to know the details of this construction for the rest of the course. The point of this lecture is just to establish that there does exist an object with the desired properties. The details of this construction will never be used. Only the definition of the real numbers that we gave will be used. Okay. So let's start. So we define a cut, C-U-T, cut, as a subset of rationals such that it satisfies three properties. The first is non-triviality, which is to say that, so let me give it a name. So it is a subset alpha of Q such that alpha is non-empty and alpha is not the entire rationals. So it is a non-empty proper subset, which is what I'm dubbing as non-triviality, just for the purpose of this lecture. The second is downward closure. So it says that if a rational number lies in the cut and Q is some other rational such that Q is less than P, then Q also lies in the cut. So anything that is smaller than an element already present in the cut is also present in the cut. This is downward closure. The cut is downward closed in this poset, which is the set of rational numbers. Okay, and lastly, this I do not have a single nice name for. This is the, lack of an upper bound inside the cut. So what do I mean? If P is in the cut, then there is a rational, a point R in the cut. Let me write it Q maybe, in the cut such that P is less than Q. So it is just saying that within the cut you cannot find an upper bound to the cut. An upper bound to the cut exists in the rationals simply because this is not the entire set of rational numbers and it has downward closure property. So yeah, so let me note that everything in the cut has an upper bound in the rationals. Each cut is bounded above in the rationals. Why is that? The reason is very simple. So say alpha is a cut, then by non-triviality we can find some element in the rationals such that this is not in the cut, because if every rational were in the cut, then the cut would not satisfy non-triviality. All right, now let some point be chosen in the cut arbitrarily. There are three possibilities. One possibility is that x is less than p, but if x were less than p, then by downward closure x would lie in the cut and x is chosen to be away from the cut, so this is not possible. If x equals to p, then it is even more not possible, because then of course x would lie in the cut. And the other possibility is that, and the only other possibility that remains therefore is, so there are some statements that I'm not writing, so therefore we must have p is less than x, and hence x is an upper bound to the cut. So very simple observation. Okay. And let us also note one more thing. I hope I'm not repeating anything, but let me write what I'm going to note. So if P is in some cut alpha, so alpha is a cut and Q is not in alpha. Yeah, so basically this is a repetition sort of the first remark, but let me write it. So if P is in alpha and Q is not in alpha, then P less than Q. This is exactly what we argued just above, so let me not justify it. This is exactly what we argued in this gray thing. All right, and let us also see an example. Let us see an example of a cut. An example is define or consider alpha as those rationals whose square is less than 2 or which are negative. So if you followed the lecture on the incompleteness of the rationals, you will see that this is a cut. So the fact that this is a cut is an exercise. All right, so the set of all the cuts is non-empty. So we define the set R, the set of all the cuts. I mean, there were much easier examples of cuts. Let me even mention that. A much easier example of a cut is let R be a rational number. Define R star as all those rationals Q, maybe I'll write Q here and R there. All those rationals are such that R is less than Q. This is also a cut. This is much easier to verify. So every rational number naturally gives rise to a cut. And R is defined as set of all the cuts. Okay. So right now it is just a set. We will endow this with an ordering and with some arithmetic properties, and then we will talk about why that thing becomes an ordered field. All right, so here are the order properties. So first we define the order for alpha and beta in R, meaning two cuts. We write this if and only if alpha is contained in beta. So the definition of the ordering is very, very simple. It is clear that this is an order, meaning it is clearly reflexive and antisymmetric, because if alpha and beta were contained in each other, then they would be equal. Transitivity also follows from this. So clearly we have a poset. But we can say much more. This is a total order. Total order on R, of course. Okay. So what do we need to show? We need to show that if we pick any two elements of R, meaning any two cuts, one of them is contained in the other. That's what it means. So let alpha and beta be arbitrary cuts. Okay. And assume that beta is not less than equal to alpha. Okay. So we want to show that there is some comparability between alpha and beta, meaning we want to show either this or that. So we assumed this does not hold, and we will end up showing that this holds, and that will finish the proof. So now since beta is not contained in alpha, this is same as saying that beta is not contained in alpha. There is something in beta which is not there in alpha. So thus, there is something in beta which is not in alpha. But then by what we observed in the previous page, this means, or let me write P. So this symbol is happening in the rationals. Even though this and those symbols look the same, they are different. Okay? So this is happening in the rationals. And this is what we observed in the previous page. This fact that if you have some rational number that is not in your cut, then that dominates everything in the cut. So we have that. And therefore, by the downward closure property of the cut beta, each element, therefore each element of alpha is in beta, right? Because if you have P in alpha, then this happens, but if this happens, then P must lie in beta by the downward closure property of beta, which means that alpha is contained in beta, which is to say that alpha is less than equal to beta by definition. So that's it. That proves the fact that this ordering is actually a total order. Any two elements are comparable. All right. So here is the most important thing, that this poset that we have now, this poset satisfies the least upper bound property, which means that everything here, that every subset of R that is bounded above has a least upper bound in R. Okay. So this is most important. This is why we are building the field of real numbers. This is why all this construction has been happening. Of course, we need to discuss the the algebraic properties of R also, but this is what we will do in detail. Okay, so fix a non-empty subset. Okay, we have a non-empty subset of the reals such that it has an upper bound. We want to show that A has a least upper bound. So let beta be an upper bound. Okay. And define gamma as the union of all the things in A. So here we are taking union over a possibly infinite set. All this means is that you collect all those rational numbers which are in at least one element of capital A. Right? Every element of capital A is a bunch of rational numbers. You collect all the rational numbers that you can find that way. That's what gamma is. So gamma is a subset of the rational numbers. We claim that gamma is a cut. So this in fact is three claims. Claim that gamma is not empty and gamma is not the entire set of rationals. So this is claim 1. Okay. So non-emptiness is clear because A is a non-empty set and hence it has some cut in it. As soon as it has a cut, this becomes a non-empty set and hence gamma is a non-empty set. So I'm not going to write anything about that. Let's talk about why it is not the entire set of rationals. So the reason is very simple. We have, since beta is an upper bound to A, we have this for all alpha in A, which is same as saying it is contained, that is the definition. And that implies the union of all the alphas is also in beta, which implies gamma is contained in beta. Now, since beta is not the set of all the rationals, beta being a cut is missing a lot of rational numbers. Therefore, gamma also misses a lot of rational numbers, and hence gamma cannot be the entire set of rationals. And we are done. So this claim is proved. Okay, we need a page. Second claim will verify downward closure. Gamma is downward closed. Okay, why is this? Fix some element in gamma. Okay, and fix something in the rationals that is less than p. We want to show that q is also in gamma. This is what it means to show downward closure. Okay, but first of all, since p in gamma, there is some element of A. Well, just so that this reasoning is very clear, let us recall what is gamma. It is the union of all the things in A. There is some element in gamma. There is some alpha naught. There is some element in A such that P is in alpha naught. So what happened? Well, gamma by definition is all those elements which are present in some element of A. That is the description of gamma. So if you choose an element of gamma, it should be present in some element of A, and let's say it's present in an element named alpha naught. Now, since alpha naught is a cut, anything less than P is also in alpha naught. Q is present in alpha naught, and hence Q is also present in gamma. That's it. So I hope this reasoning was clear. Lastly, we will show the property 3, which is to say that you cannot find an upper bound of gamma inside gamma. Gamma does not have an upper bound of itself. Okay. So, suppose we have some element of gamma arbitrarily chosen. We want to show that P is not an upper bound to gamma. So, want to find some Q in gamma such that P is less than Q. This would finish the proof because then P wouldn't be an upper bound of gamma. Alright, so again, let alpha naught in A be such that P is in alpha naught, just like in the previous claim. Since alpha naught is a cut, by property 3 applied to alpha naught, there is some element such that P is less than Q. But Q, since Q lies in alpha naught, Q also lies in gamma, and we are done. Okay, so we have proven all the 3 claims, and what we have done so far is that Gamma is a cut. That is all that we have done so far. Now the point is that we want to show, our claim is that gamma is the least upper bound of A. So that's the final thing. We claim that least upper bound of A. Okay. Clearly gamma is an upper bound of A. By definition of gamma is an upper bound of A. Just think about it. So to prove that it is the least upper bound, fix some upper bound of A. So let delta be an upper bound of A. We want to show that gamma is dominated by delta. Once we do this, we will be done. But since delta is an upper bound of A, delta contains everything in A. But then alpha is less than equal to delta for all alpha in A, which is to say that alpha is contained in delta for all alpha in A, and hence the union of all the things in A is contained in delta, which implies gamma is contained in delta, which is to say that gamma is less than equal to delta, and we are done. So this finishes the proof that the set of real numbers is a totally ordered set with the least upper bound property. So far, we haven't talked about the algebra of the real numbers, which is the topic of the remaining lecture. Okay. So let alpha and beta be two cuts. We want to define their addition and multiplication. The addition is simple, while the multiplication will be a bit convoluted, but I don't think that can be helped. So define their addition as follows. Okay, so this is how we define the addition. And before we define the multiplication, we need to define a few things. So we define 0 star as all those rationals which are less than 0. This is nothing new. We saw this. For every rational, there's a natural cut. So 0 is a rational number and for which we have a natural cut. Okay. We define R plus as all those cuts which are strictly dominating 0 star. Okay. And for any cut, define alpha bar as follows. So it's those rational numbers for which there exists a positive rational such that this is not an alpha. So just think about what alpha bar is. If we hadn't written this, that there exists a positive rational such that, basically suppose we had just written minus p is not in alpha. Just think about what that thing is and then you will understand better what is alpha bar is. Okay. So all of this, this was already defining the addition. All of this is being said so that we can define multiplication. So for multiplication, we will have to take a convoluted route. So for two elements in R plus, their multiplication is defined as follows. Define alpha times beta as all those rationals which are dominated by R and S for some R in alpha but positive and for some S in beta but positive. So note that if you have something in R plus, if alpha is a cut in R plus, then it will contain positive rationals. Same for beta. So this is a meaningful thing. This is how we define multiplication, but we need to define multiplication for any two cuts. So now for two cuts alpha and beta, define alpha beta as follows. So it has already been defined when alpha and beta are both positive. So in case both are negative, we define it like this. If one is negative, one is positive, and 0 if... Okay, so a bit convoluted, but this is how we do it. And even before I wrote everything, I should have said that here one should check that alpha plus beta is a cut. Therefore, it lies in the set of real numbers. And here, when we defined alpha beta in R plus, here also check that this is a cut. Okay, so when we defined this for any arbitrary cuts, note that here all the time we are taking, these two are product of two positive cuts, and hence this is a cut. Here is also this is also a product of two positive cuts, and we have taken bar of it. So that should also be said that this has to be checked to be a cut. All right, these are exercises. Okay, so we have defined addition and multiplication. Before we continue, let me also say this is 1 star. This is nothing new, but good to say it. Okay, so addition and multiplication have been defined, and one has to check. These are exercises. Check associativity. So let me just say associativity and commutativity of the addition and multiplication just defined. Okay. And second is check that 0 star is the additive identity, 1 star is the multiplicative identity. Okay. Check distributivity. For additive and multiplicative inverse, check alpha bar is the additive inverse of alpha for any cut. So alpha bar is nothing but minus alpha. I just wrote it as alpha bar earlier. Okay, and similarly check the existence of multiplicative inverse of non-zero element. Okay. I think I'm not missing any field axioms, so this will verify that this is a field. If I'm missing any field axioms, just verify them also. So this is a field once you do all these steps. But most importantly, check that this thing is an ordered field. Okay. So these are exercises. You don't really need to do them. As I said, this construction will be irrelevant. We just need to know that the real numbers exist, which is why we are doing all this. So you can, in some sense, ignore this lecture entirely, and that's okay. One last remark is that the natural copy of Q in R is as follows. You can just put Q inside R by sending every rational to R star, which we defined earlier. So this is your natural copy of the rational sitting inside the reals. Okay, I think I'm not missing anything. If I'm missing anything, then well, I've missed it. What can I do? This lecture is anyway not the most important one. So let me just end it here. As usual, like, comment, share, subscribe, and I will